For the past few years, artificial intelligence has been obsessed with one thing: bigger. Bigger models, more parameters, longer context windows, more compute. The AI industry believed intelligence scaled with size, and to a large extent, it did. But then a new constraint emerged: speed. It didn't matter how smart your model was if it responded slowly. It didn't matter how powerful your reasoning was if inference costs were unsustainable. And as AI applications moved from demos to real-time products, speed became the real battlefield. Now, a company called Inception claims it has shattered that barrier. Their new model, Mercury 2, isn't just another large language model. It's something fundamentally different. It's the first production-ready diffusion-based reasoning model. And according to early benchmarks, it might be one of the fastest language models ever deployed. Mercury 2 is a large language model developed by Inception Labs, but calling it a large language model doesn't fully capture what makes it unique. Unlike traditional transformer-based LLMs, which generate text one token at a time in sequence, Mercury 2 uses a diffusion-based approach to language generation. That's important, because traditional models are autoregressive. They generate token 1, then token 2 based on token 1, then token 3 based on tokens 1 and 2, and so on. This sequential nature creates latency. No matter how powerful the hardware is, generation must happen step by step. Mercury 2 changes that dynamic. Instead of predicting the next token in a strict sequence, it generates drafts of text in parallel and iteratively refines them. Think of it like sculpting. Instead of writing a sentence word by word from left to right, it creates a rough version of the entire output and then improves it over several refinement steps. This diffusion-style generation enables parallelism, and parallelism unlocks speed. The headline number that caught the industry's attention: 1,000 tokens per second. Some independent analysis platforms report throughput even exceeding that under certain configurations. To put that in context, many leading LLMs operate between 50 to 200 tokens per second in real-world conditions. Even speed-optimized models struggle to consistently reach 300 to 400 tokens per second without sacrificing quality. Mercury 2 claims performance roughly 5 times faster than many speed-optimized transformer models. That's not a small improvement, that's a step change. And speed isn't just about convenience, it changes the kinds of applications you can build. In the early days of LLMs, latency was tolerated. Users expected a few seconds of waiting. But now, AI is embedded into live coding copilots, autonomous agents, real-time data dashboards, customer support bots, and interactive search experiences. In these systems, delay breaks immersion. If an AI agent needs to reason through multiple steps, calling tools, querying APIs, generating plans, latency compounds. What takes 1 second per step becomes 10 seconds over 10 steps. That's unusable. Mercury 2's speed enables something critical: real-time agent loops. It allows an AI system to think, act, observe, and respond almost instantaneously. And that changes product design entirely. To understand the breakthrough, we need to go deeper. Diffusion models first became famous in image generation. Models like Stable Diffusion generate images by starting from noise and gradually refining toward coherence. Mercury 2 adapts that principle to language. Instead of predicting text left to right, it starts with a noisy representation of the full output and refines it over multiple passes. The key advantage: refinement steps can be parallelized. Parallelism reduces latency dramatically on modern hardware. This architecture also changes how reasoning unfolds. Rather than committing to early token choices and being constrained by them, the model can revise across the entire output. This potentially improves coherence and logical consistency. However, diffusion-based language modeling is still relatively new. Mercury 2 is one of the first serious attempts to productionize it. According to independent benchmarking platforms, Mercury 2 demonstrates strong reasoning performance relative to its size class. While it may not match the largest frontier models on every intelligence benchmark, it offers a compelling trade-off: high reasoning capability combined with extreme speed. In practical terms, you may get 90 to 95% of the reasoning performance of leading models at a fraction of the latency. And in real-world applications, that trade-off often wins, because users value responsiveness. Let's address the comparison question. How does Mercury 2 stack up against Gemini Flash variants, Claude Haiku, GPT-4 class models, and other speed-optimized models? Most transformer-based models rely on autoregressive decoding. That means no matter how optimized the kernel is, they cannot escape that architectural constraint. Mercury 2, in contrast, escapes that architectural bottleneck. In raw throughput tests, it dramatically outpaces many mainstream API models. However, frontier-scale models trained with massive parameter counts still hold advantages in certain advanced reasoning tasks. The question becomes, do you need maximum reasoning depth, or do you need speed at scale? Mercury 2 is optimized for the latter. Speed affects cost. Inference cost scales with compute time, GPU utilization, memory bandwidth, and batch efficiency. If a model completes inference 5 times faster, it consumes fewer compute cycles per request. That means lower cost per query. And at hyperscale, millions or billions of requests per day, small cost reductions compound dramatically.
For startups and enterprise customers, lower inference cost means higher margins, lower subscription prices, and wider AI adoption. Speed isn't just technical, it's economic. Another strategic decision. Mercury 2 is designed to be compatible with OpenAI-style APIs. That lowers friction for adoption. Developers don't need to rebuild entire stacks. They can swap models with minimal integration effort. That's smart positioning, because technical superiority means little if switching costs are too high. Here's where Mercury 2 becomes especially interesting. Agentic systems require multiple iterative reasoning steps. For example, understand the request, plan actions, call external tools, process tool results, revise plan, generate final output. Each step involves LLM calls. If each call takes seconds, agents become impractical. If each call takes milliseconds, agents become viable. Mercury 2 speed may accelerate the rise of autonomous AI systems that operate fluidly in real time. One of the most overlooked aspects of Mercury 2's launch is how it reframes the scaling conversation. For years, the dominant belief in AI research was that intelligence primarily scales with parameters and data. Bigger clusters, bigger budgets, bigger training runs. But Mercury 2 shifts the focus from brute force scaling to architectural efficiency. Instead of competing purely on size, it competes on how computation is organized. That's a subtle but powerful pivot. It suggests that the next wave of AI progress may not come solely from trillion-parameter models, but from smarter ways of generating and refining language. The diffusion approach fundamentally changes how we think about text generation. Traditional transformers commit to each token sequentially. Once a token is generated, it becomes part of the irreversible past. But diffusion-style models treat generation more like iterative drafting. They can revise across the entire output field. That's it. If you like this breakdown, make sure to subscribe to the channel. Catch you in the next one.